Great. So thank you for sticking around for the very last talk of the week here. I'm happy to present Rahul, who will be telling us more about kernel methods in causal inference.
Yeah, thank you, Chris. So the title for today is Kernel Methods for Long-Term Causal Inference. My name is Rahul. I'm a research fellow here at Simons, and I'm also a PhD at MIT. Motivation for this project is Project STAR, which stands for the Tennessee Student-Teacher Achievement Ratio Experiment, in which a cohort of kindergartners in 1985 were randomly assigned to either small or regular class sizes. We see in the picture one of the small class sizes, which was 13 to 17 students, and that's smaller than what was considered regular in the state of Tennessee at the time. This was one of the large labor market interventions we have with randomization, and it involved about 11,600 students and teachers. With randomization, we have identification, and we can ask what were the effects. So Kruger in 1999 studied the effects and the duration of the experiment. It was 4 years. It followed these kindergartners through 3rd grade. And in the figure, we're looking at counterfactual distributions of test scores. So the dashed line is the counterfactual distribution of test scores if all of the students were assigned to the regular class size, but the filled line is the counterfactual distribution of test scores if they're all assigned to small classes. And we can see it's pushed out a little bit to the right. Roughly a decade later, Chetty and co-authors took this experimental data set, which was, remember, only 4 years of data, and merged it with administrative data, which means tax returns and things like that, to follow those kindergartners after they've reached the age of 27. And we can look at these medium-term variables like college quality and maybe earnings at 27. In this figure, again, we're looking at counterfactual distributions. This time, we're looking at distributions of college quality. And the blue curve is the counterfactual distribution of college quality in the thought experiment in which all the students were assigned to the regular class size. The green curve is the counterfactual distribution if they're all assigned to the small class size. And these just need to be normalized. Near the end of the paper, the authors write, we conclude by using our empirical estimates to provide rough calculations of the benefits of various policy interventions. These cost-benefit calculations rely on several strong assumptions. We assume that the percentage gain in earnings observed at age 27 remains constant over the life cycle. And I think there are several interesting ideas in these few sentences. One idea is that if we really want to do a cost-benefit analysis of Project STAR, we need to extrapolate beyond even what we get by merging with administrative data. We need to extrapolate from earnings at 27 all the way up to perhaps earnings at the age of retirement at 65. Another interesting idea is that we need assumptions to do that extrapolation. And this assumption, this very strong one, is maybe one we're uncomfortable with. What I want to take away from the discussion of Project STAR is that experimental data, it's very expensive to collect and therefore typically short-term. So Project STAR only lasted 4 years and it cost the state of Tennessee $12 million. Even if we have special sworn status and can merge our experimental data sets with administrative ones, still that only takes us to the medium term, up to age 27. But that's not quite everything we want to learn because cost-benefit analysis depends on the long term. We might be interested in asking which social policies pay for themselves. Maybe Project STAR cost $12 million, but those students went on to become high earners and high taxpayers, and maybe the state of Tennessee made back much more than 12 million. There's also this discomfort with the constant effect over time assumption. And indeed, empirically, we see that test score effects fade over time. So maybe earnings effects fade over time too. And a big question is that I'll try to address today, what can we say about long-term effects in a principled, but also ideally flexible way? The main idea is that to think about the long-term effects, we're going to combine data from 2 data sets. First, an experimental data set that's like the Project STAR data set as merged with the administrative data that has the treatment and these medium-term variables. And second, an observational data set that has medium-term variables and long-term ones. This is something like an appendix table that this paper has, which has correlations between earnings at 27 and earnings later on. In this work, I'll propose kernel estimators that have closed-form solutions and that come with strong finite sample guarantees. For treatment effects, I'll prove long-term treatment effects, I should say. I'll prove root-end consistency, finite sample Gaussian approximation, and semiparametric efficiency. For long-term dose responses, I'll prove uniform consistency with finite sample rates. And for long-term counterfactual distribution, I'll prove finite sample convergence in a certain norm, which implies convergence in distribution. Overall, my goal in this project is to provide a unified framework for flexible estimation of these long-term causal parameters. The key assumption I'll make today is that a certain conditional distribution is smooth and a certain regression is smooth. In the paper, I'll further characterize an idea of multiple spectral robustness in the semiparametrics, which is another take on double sparsity robustness, which has become quite popular in semiparametrics. In this work, I build on many that came before. First and foremost, on the long literature of statistical surrogates, which refers to when you have an experiment and they're just these short-term outcomes, which are kind of surrogates for the long-term variables we really care about. There's a long history in statistics and biostatistics that's recently been revived, in which different authors propose different identifying assumptions and different takes on the problem. I'll also build on existing semiparametric theory, in particular principles from debiased machine learning, which distill rate conditions which are sufficient for the good properties we'd like. A big step in this direction is from Chen and Wirtz-Waller, who characterized the multiply robust moment function. An important paper to mention is the Batacci et al. Paper, in which the authors prove these good properties for estimators that impose linearity and separability. And one thing I'm going to try to do in this paper is relax those kinds of aspects because, strictly speaking, they aren't required for identification. In terms of nonparametrics, again, I'll build on papers that came before. An important one here is Das, Nui, Vela, 2003, which is about structural functions in the presence of sample selection. A little later on, we'll see the connection to the sample selection problem. I'll also build on previous work that provides uniform analysis for causal kernel methods, but for much simpler problems like dose responses and heterogeneous treatment effects in just the usual treatment effect setting. The key algorithmic technique is going to be something called a sequential mean embedding, and that'll feature prominently in both the nonparametrics and in the semiparametrics, and we'll walk through that together. Overall, in this work, the estimators and their guarantees are new. So let's return to what is the data setting. Well, we have an experimental data set. This is like the one in the main text of the Chetty et al. Paper, where it's the project star data set with individuals. Specifically, we see their demographics, their class size, and also their earnings at 27. We do not get to see their earnings thereafter. For example, their earnings at 65. Meanwhile, we have another data set, perhaps using our special sworn status, which is observational. So it's students who did not take part in Project STAR. And for them, we have their demographics, their earnings at 27, and their earnings at 65. And we're interested in reasoning about what was the effect of class size on earnings at 65, even though we have one data set in which we're missing earnings at 65 and another in which we're missing class size. From here on, I'm going to use the language of covariates, treatments, surrogates, and outcomes instead. So we have an experimental data set with covariate X, treatment D, and surrogate M, but we're missing the outcome Y. And we have another data set where we have the covariate X, the surrogate M, the outcome Y, but we're missing the treatment D. And we're interested in reasoning about the effect of the treatment on the outcome. The first step is to define a fused data set, by which I mean, let's take the rows from the experimental data set and concatenate them with the rows from the observational data set. Then let's take a look at what happens to the columns. Well, the covariate columns are exactly as before because we see covariates in both data sets. The treatment column is a bit interesting because we do see treatments for the experimental group, but then we have NAs in the observational group. And I'll follow the convention of overriding those NAs as zeros. We have the surrogate columns, which are as before. The outcome column is interesting again because there are NAs for the experimental group, but we have real values for the observational group. So in the fused data set, we get to see covariates. We get to see this fused treatment variable D prime, which is sometimes NAs. We see the surrogate columns, and we see these fused outcomes, which I'll call Y prime. Written this way, I think it becomes quite clear the connection to classic sample selection problems in the spirit of Rubin 76 and Heckman 79. For identification, I'm going to quote an existing result from Athey et al. And my focus will instead be on estimation and inference. So here are some identifying assumptions. There are three categories of them. First of all, SUTFA, kind of ruling out network effects. Next, assumptions about the treatment mechanism. And we only see the treatment in the experimental sample, so these assumptions are all conditional on being in the experimental sample. We have that treatment is confounded, that is conditional on covariates, it's as good as randomly assigned. We have surrogacy, which is arguably the strongest assumption, conditional on covariates and surrogates, treatments independent of outcome. And then we have an overlap condition. Next, we have assumptions about the selection mechanism. The first of which is precisely Rubin's missing at random assumption, that conditional on covariates, selection is as good as randomly assigned. Next, we have comparability, and finally, selection overlap. For today, let's consider the causal parameter I'll call theta naught with argument little d. And that's the mean potential outcome in the thought experiment in which we overwrite the treatment to be the value little d. Athey et al. Proved that under the stated assumptions, this causal parameter can be expressed as the very interesting double integral we see on the slide, which has several objects in it. It has gamma naught, which is a function. It has a conditional distribution, and it has a marginal distribution. Now, where do these come from? Well, the conditional distribution is from the experimental sample, where we do get to see surrogates and treatments. The function is a regression that we get from the observational sample, where we do get to see the outcome and we do get to see the surrogates. And finally, the marginal distribution can be from both of these samples. I want to point out the sense in which, in this expression, everything's very linked. So in that final integral with the marginal distribution, it's with respect to x, which appears in both the function gamma naught and in the conditional distribution, which we're using to integrate gamma naught. So it's very non-separable and perhaps not obvious how one might be able to estimate. There are also a few different perspectives we can take on what this integral equation really means. If we take treatment to be binary, then on the left-hand side, we have a scalar, which is like a treatment effect. And on the right-hand side, we see a nonlinear functional, which quite resembles Robin's G formula. Another point of view we might take is if treatment is continuous. So instead of there just being regular or small class sizes, there's really the number of students who are in your class. In such case, on the left-hand side, we have a function. And on the right-hand side, we're integrating this function, this regression, according to a conditional and then a marginal distribution. The idea of integrating out arguments of a regression is sometimes called a partial mean in econometrics. And here we have a sequential partial mean. Yes, please.
Very, very brief comment. Sorry. You mentioned it looks like the G formula. It also looks like the mediation formula, right? Because of the dot factorization of the different treatments, except that this is just the indicator of the domain here, right?
I completely agree. And in another work, I argue that mediation analysis, dynamic treatment effects, and this long-term effect problem all are the same class of nonlinear functions and the same semiparametric theory. When I opened, I had these figures which were counterfactual distributions. In such case, on the left-hand side, the causal parameter is a distribution, which is indexed by a treatment value little d, which could be discrete or continuous. And so on the right-hand side, instead of integrating a function, we're integrating a distribution gamma naught. In such case, instead of being a partial mean, it's like having a partial distribution, or pushed even further, a sequential partial distribution. For the rest of the presentation, I'll focus on the dose-response perspective, but in the paper, I'll cover all three. And I'll also extend analysis to different causal parameters, such as for subpopulations, like just the students who are in the experimental sample, like in Project STAR, and also alternative populations. What if Project STAR didn't take place in Tennessee, but rather here in California? For estimation, I'm going to bring in the technology of the RKHS. In particular, I'm going to assume that this function gamma naught is in an RKHS that is a tensor product. So what do I mean by that? It's like I choose features for selection, phi g, features for covariates, phi x, and features for the surrogates, phi m, and then take the tensor product of those to define the features I'm interested in for the function gamma naught. Formally, the property I'm using here is that if you take the product of three kernels, you get a new kernel. With this construction, I'm able to express the causal parameter, which is an interesting and complicated double integral, in a very concise way. If we believe that gamma naught is in that RKHS, then the causal parameter can be expressed as the inner product we see. It's an inner product between the regression gamma naught and something that's quite interesting, this mu3, which encodes sequentially both of those distributions. First of all, we encode the conditional distribution by writing a conditional mean embedding. Essentially, we're reweighting the surrogate features by the conditional distribution, and that's the way that we're going to embed it. Next, we need to embed the marginal distribution. And because these two conditional distributions involve x, we need to first take the outer product with features of x before doing that embedding. Altogether then, we're getting gamma naught from the observational sample, and we're going to multiply it with this sequential embedding, which involves a conditional distribution from the experimental sample, and then a marginal distribution, which could be from both. This is a bit of an abstract slide, but it actually gives us the blueprint for estimation, because it tells us if you just do a nonparametric regression, like a kernel ridge regression, that'll give you gamma naught. And then how do we get mu3? Well, first you need to do mu1, which is something like a generalized regression. Instead of having a scalar outcome, we have features of surrogates as the outcome. So that's a generalized kernel ridge regression as well. Next, we need to do just some kind of empirical averaging, right? It's a marginal distribution. And finally, we take the product and we're done. Indeed, this algorithm I'm describing verbally will have a closed form solution by the usual representer theorems. And it's pretty simple to describe. It's just 3 steps. First of all, we'll calculate our empirical kernel matrices, which are n by n. Second of all, we'll make these vectors, which are of length n, which are essentially the way that we're doing that generalized kernel ridge regression for the conditional distribution. We can see how this is really like a generalized kernel ridge regression of features of surrogates. So that's the features of m on the other variables. And it has a ridge regression regularization. That's what I'm going to call lambda experimental, because this is using observations from the experimental sample. And then in the next step, we see that there is a more familiar kernel ridge regression of the outcome on variables. That's from the observational sample, so I'll call that regularization parameter lambda observational. Finally, we have the marginal distribution to average over, and that's the averaging we see out front. So stepping back, there are 2 sets of hyperparameters here. There are ridge regression penalties, lambda experimental and lambda observational, for which we can derive theoretical values that balance bias and variance. But also it turns out that leave one out cross-validation has a closed form solution because we're doing ridge kind of regressions here. And so you only have to compute the estimator once. There are also hyperparameters of the kernels, but for those we have well-known heuristics. For Gaussian kernel, for example, we would use the median interpoint distance. So what can we prove about this estimator, which we saw in 3 steps? Well, recall that this was the causal parameter we're interested in, and I'll place 4 assumptions. First, some weak regularity conditions on the original spaces. Second, some weak regularity conditions on the RKHSs. And then 2 more substantial conditions, which are really about smoothness. So smoothness of the conditional distribution and smoothness of the regression. Let's get the regularity conditions out of the way. Well, we'll require that the treatment covariate and surrogate spaces are Polish, and that's really flexible. So these variables could be reals, texts, images. There's really a lot of flexibility here. I'll also impose that the outcome is bounded just to make things shorter. That can be relaxed. For the RKHSs, I'll impose that the kernels are continuous and bounded, their feature maps are measurable, and that certain kernels are characteristic. That just means that these embeddings in which I'm encoding the distributions in the RKHS, that's an injective mapping. So there are unique RKHS representations. Fortunately, all these conditions hold for all the usual kernels used in practice, like the Gaussian, spline, and Sobolev kernels. The substantial assumptions I'll place are about smoothness, a smoothness about the conditional distribution and about the regression. For the conditional distribution, it's helpful to reparameterize it as a conditional expectation operator that's smooth. And I'll call it smoothness parameter C experimental, because this is going to be estimated with experimental observations. For the regression learned from the observational sample, I'll call it smoothness parameter C observational. To get intuition for these smoothness parameters before we see more formally what they mean, they're really approximation error assumptions that are used to analyze the bias from the ridge regularization. And they're essentially saying that certain statistical targets are well approximated by the top eigenfunctions of the kernel. These are called source conditions, both in the statistical learning theory literature and in the econometrics literature.
Quick question. I think I understand the targets will approximate with the top eigenfunctions of its kernel. What I don't understand is the next line, which says that the target is in the interior of its RKHS. Like if we have a linear kernel, then I think like every point is in the interior. What is it? Could you elaborate what you mean here?
Yeah, thanks. That is, I agree, a loose statement. And I think this slide will be clarifying what I did.
Thanks.
So a special case of an RKHS is a Sobolev space. And let's consider the Sobolev space HS, where S is the number of square integral derivatives and P is the dimension of the input space. The Sobolev space is an RKHS if and only if S is greater than P over 2. And that's a very familiar condition from functional analysis. Suppose we use that as our RKHS for estimation. Meanwhile, the truth, what we're trying to estimate, is in the Sobolev space with S0 degrees of smoothness. Then by C, I mean the ratio of S0 over S. So it quantifies the additional smoothness of the statistical target relative to the hypothesis space we're using for estimation. So I was being loose when I said in the interior. It's like, it's a little smoother than it needs to be. In my analysis, I'm going to require that C is greater than 1, which is like saying that S0 is greater than S is greater than P over 2. So it's a somewhat strong smoothness condition. Please.
For Gaussian RKHS, what would you mean by citing interior because they are infinitely differentiable?
Great. So I could similarly characterize what this means in the context of the Gaussian kernel. Maybe I can share that with you offline. We'll do it next time. Under these stated conditions, and if we calibrate the regularization to balance bias and variance, we get a result like we see on the slide, where n is the sample size, C experimental is the smoothness of the conditional distribution, and C observational is the smoothness of the regression. This rate is at best n to the minus a sixth by setting both of those smoothness parameters up to 2. To interpret the results some more, on the left-hand side, we have a soup norm guarantee, which is going to be uniform across all treatment levels, across all classroom sizes. And that's stronger than a mean squared error guarantee, which is kind of on average across treatment levels. And I think that's important because it encodes caution if we're going to use results like these to inform labor market policy. This rate is somewhat slow. It's at best n to the minus a sixth, but in the result I put on the slide so far, it's using relatively minimal assumptions. One could place stronger assumptions to get faster rates. And it doesn't directly depend on data dimension, but that's because we are smooth enough relative to dimension. When it comes to semiparametrics, I'd also like to point out that it's not too slow in the sense that minus a sixth plus minus a third is minus a half. So you get the sense of where this multiple spectral robustness idea will come up. In the paper, I provide exact finite sample rates. So results in the form with probability 1 minus delta, the bound and soup norm is something. To conclude in this work, I propose a family of estimators for long-term causal inference that are relatively easy to implement because they have closed form solutions. I also provide strong finite simple guarantees for the treatment effects, dose responses, and counterfactual distributions. My big picture goal is to provide something of a bridge between this idea of long-term cost-benefit analysis and between kernel methods to answer questions like which labor market policies pay for themselves. And this work is part of a broader agenda where the main idea is that causal inference presents us with very interesting and challenging integral equations, while kernel methods provides us with the techniques to solve them. I'd love to talk more, and here's my email address.
Are there any questions for our speaker here? I have one. If you go back one slide, you have these penalty terms that show up in the regressions. These like lambdas here. I guess you could, we don't know the smoothness, beforehand, but I assume we could like find what the best lambdas are using CrossFit or something like that. Do you guys have like theory for that, or do you have a sense of how that might work out or change the rates or the rates for the Yeah.
Yeah, that's a great question. So just like leave-without cross-validation has a closed form, so does generalized cross-validation. And that's kind of an old and classic result. And for certain RKHSs, we know that generalized cross-validation is asymptotically optimal. So it will trade off bias and variance like it should. I think a characterization that's more general for kind of all RKHSs is an interesting direction to argue that generalized cross-validation will kind of work for all RKHSs. Yeah, that's an interesting direction to go in.
Awesome. I have one more question, but I'd like to ask if anyone else has a question here. And it'll be mine. My other question is with this experiment, this TAR, I'm wondering if you happen to know what they were interested in investigating with these small classroom sizes, because the story that you gave of knowing what their what the effect is on their earnings at 65, that makes sense to me. But I'm kind of thinking like, oh well, did the STAR people have? I mean, did they have the methodology to do that? Were they thinking about that? What were they? So I guess I wonder if you know what their goals were, and I'd love to hear more about that.
Yeah, so Project STAR was spearheaded by a former teacher, and she was particularly interested in what's the right class size we should have in our schools in Tennessee. And it was designed to be just for these 4 years. So it's with some creativity that we were trying to extrapolate beyond that. And I think that's kind of representative of what we often do in experiments, where we have a certain scope and a certain budget, and so we do something. And then after the fact, we try to extrapolate, we try to glean something more than that. But the original intention was really just about the effect of kindergarten size at early age.
Awesome. Yes, another question here.
The application of the surrogate. So one assumption I think in the surrogacy is that you don't need unobserved confounding between the surrogate and the outcome. So is that like something reasonable for the STAR application or for the Project STAR?
Good question.
Should we worry about things that we're not controlling that are directly affecting the medium term and the long term?
Yeah, that's a great question. I think maybe we would need to talk to some domain experts in education research to see if they believe the assumption. Fortunately, if we don't believe the assumption, there are other identifications that we have with like proximal setting, in which case, instead of having kind of regressions, we'll have confounding bridges, and there are kernel methods for those as well. So the general architecture of these techniques will absolutely go through.
So I have a question about the rate you have here on the slide. So I understand that this is standard in some communities, but not in my community. So so the order depends on something that you don't know. So I wonder, right? So how do you use this to say evaluate the STAR policy? Like if it depends on the instance, you play some extra assumption. What do you do?
Yeah, that's a great question. So when it comes to semiparametrics, it's if we're willing to take a stand on how smooth things are, it ends up being root n. So we don't need to, and we can estimate and provide a confidence interval that will have asymptotically relative nominal coverage and all that. For nonparametrics in the finite sample, I think it's a good question. I think that brings our attention to the problem of uniform inference, in which case we could provide a uniform confidence band, which has some interpretation. I agree that a result like this is perhaps not strong enough for really making policy recommendations.
Great. Are there any more questions here? Well, if not, let's thank the speaker. And I think that concludes the workshop for this week. So thank you everyone for